FIFA World Cup 2026 is officially underway, but behind the scenes, billions of dollars are being spent on a strange mission.
Burying America's multi-million-dollar artificial turf under layers of real soil, just to meet strict tournament rules.
It raises a fascinating question. How did a synthetic surface, completely born in heavy industrial factories, come to dominate? But unlike real Earth, nothing here ever grows, withers, or dies. It's an indestructible engineering marvel, designed to survive brutal impacts and extreme weather for years. So, what chemical recipe makes this artificial plastic grass so perfect? And how do factories manufacture a surface that can outlast nature itself? Artificial turf first appeared in the United States during the early 1960s, when indoor stadiums faced a simple problem. Natural grass struggled to survive inside enclosed arenas with limited sunlight and airflow.
Engineers turned to an unexpected industry for help.
The carpet industry already possessed the knowledge to melt plastic, form fibers, and securely integrate them into fabric backings.
By adapting those techniques, they created the first generation of synthetic grass. By adapting those techniques, they created the first generation of synthetic grass. As artificial surfaces improved, FIFA introduced its quality program in the early 2000s.
To ensure synthetic fields performed more like real grass.
Today, the global artificial turf industry is worth more than $7 billion.
And what started in one Texas stadium has spread to sports facilities all over the world. And what started in one Texas stadium has spread to sports facilities all over the world. Most manufacturers use polyethylene because it stays flexible while resisting weather and heavy use.
Workers add green pigments, UV stabilizers, and performance additives before sending everything into a giant extruder.
Inside the machine, rotating screws slowly push the material forward, while temperatures rise to around 400 to 500 degrees Fahrenheit.
The pellets disappear and transform into glowing streams of molten plastic. Next, the molten material flows through steel spinnerets, filled with hundreds of microscopic openings.
Long green strands emerge continuously and plunge into cooling tanks. Water instantly solidifies the fibers while keeping them flexible.
Powerful drawing rollers then stretch the fibers by as much as 30 to 40%. Why stretch them at all? Because stretching aligns the polymer molecules inside the plastic. Without this step, the blades would bend and flatten much faster after repeated use.
After strengthening, winding machines wrap the fibers onto giant spools that stand nearly as tall as the workers beside them.
Several spools unwind together to form thicker yarn bundles that improve resilience.
The yarn then enters one of the most fascinating machines inside the factory. The tufting machine works like a massive sewing machine.
More than 200 needles move up and down in perfect rhythm, while the backing material slowly advances underneath.
Flights. The rapid clacking sound fills the room as thousands of stitches appear every minute. Below, rotating knives cut the loops.
At this point, the turf finally starts to take on a familiar look. A green carpet gradually forms.
Dense, textured, and building inch by inch. This stage determines blade height, spacing, and the overall appearance of the field. And a question arises. How many stitches do you think are hidden in a single square yard of turf?
At this stage, the grass blades still aren't permanently secured. The turf moves onto the coating line. where heavy rollers spread latex or polyurethane across the underside.
Football cleats create tremendous pulling forces. Without a secondary backing layer, the blades would gradually loosen and fall out.
Next, the material enters enormous curing ovens. Some drying tunnels stretch nearly 50 meters long.
Giant fans circulate hot air, while engineers carefully monitor temperatures to avoid damaging the fibers.
Now the focus shifts from manufacturing to real-world performance. Before leaving the factory, technicians inspect pile height.
Specialized testing machines repeatedly compress the turf to simulate years of football traffic.
Once approved, giant rolls leave the factory and head to construction sites.
Some rolls weigh several thousand pounds and require forklifts for loading and positioning. Installation crews first prepare a compacted stone base. Many professional systems also include a shock pad beneath the turf to absorb impacts and reduce stress on athletes. Workers unroll the giant sections, align the seams, and secure them with adhesive seam tape.
Brushing machines then distribute silica sand and rubber infill deep between the blades.
These materials support the fibers, improve traction, and help control ball behavior.
Why does FIFA certify the entire field instead of just the turf itself?
Because the playing experience depends on every layer working together.
After installation, engineers perform a series of field tests that measure ball roll, ball rebound, shock absorption.
Only then can the complete system qualify under the FIFA quality program.
From above, the finished surface looks like ordinary grass.
But beneath every pass, tackle, and goal lies decades of plastic engineering, textile technology, and manufacturing techniques. Everything starts with a bare piece of land. Excavators remove the existing soil while bulldozers push massive amounts of earth across the site. Workers lay red heating pipes on a gravel base, ensuring the grass can grow even in cold weather. What most people see is just a normal soccer field.
A wide green surface, perfectly even, ready for play, whether it's a local match or a stage as big as the 2026 World Cup in North America.
But under that simple layer of grass, something very different is going on.
Because these fields are expected to handle extreme conditions, heavy rain, constant play, and rapid recovery between matches,
without breaking down or turning into mud like a natural lawn.
So what is really happening beneath the surface of a soccer field that allows it to perform like this at the highest level of the game?
For most of football history, natural pitches were simply grass, growing on native soil.
Early clubs in England during the late 1800s cleared open land, leveled the surface, and relied almost entirely on the weather.
As football became more professional in the 20th century, groundskeepers introduced drainage systems, sand-based soils, and scientific turf management.
Maintaining a pitch gradually evolved from basic lawn care into a specialized profession.
Natural grass fields became increasingly important in the United States after the 1994 FIFA World Cup.
And the launch of Major League Soccer in 1996.
Today, more than 16 million Americans play outdoor soccer each year, and thousands of soccer fields operate across the country.
What looks like a simple green field today is actually the result of more than a century of evolution beneath the surface.
Everything starts with a bare piece of land. Excavators remove the existing soil while bulldozers push massive amounts of earth across the site. From ground level, the area may appear perfectly flat, but engineers are carefully creating subtle contours that most people would never notice.
Why not build the field completely level?
because standing water is the enemy of natural grass.
Even small puddles can affect ball movement and damage the turf. FIFA recommends designing the pitch profile around local drainage conditions and climate patterns.
Surveyors constantly check elevations with laser equipment. A difference of just a few inches can create problems later. If this foundation isn't correct, every layer above it suffers.
Workers cut long trenches across the pitch in a precise herringbone pattern.
Inside each trench, perforated HDPE drainage pipes are laid. These pipes look simple, but they act like the lungs of the entire field. Crushed stone is poured around the pipes. Then, layers of coarse sand are added to filter water before it enters the drainage system. A properly designed drainage network allows games to continue even after heavy rain.
Engineers inspect pipe spacing and slope before covering everything with aggregate.
If one section sits too high, water can collect underground and create long-term problems.
A carefully blended root zone mix is spread across the field using conveyor spreaders.
The material flows like dry sand, but contains a precise balance of silica sand, organic matter, and nutrient stabilizers.
Laser screed machines glide over the surface, shaving high points and filling low points.
The goal is almost unreal, a tolerance measured in millimeters across an entire football pitch.
The texture changes underfoot. It shifts from loose granular soil to a firm, structured medium designed for one purpose: root growth. Ground technicians perform moisture tests using probes that sink into the layer, checking oxygen flow and water retention.
Now the field begins to turn green, but it is still fragile, almost temporary.
Massive rolls of pre-grown sod arrive on pallets. Each roll is cut from specialized turf farms where grass has been cultivated under controlled conditions for months.
The rolls are unrolled across the pitch like giant green carpets. Workers align each seam carefully. A gap of even a few millimeters would become visible lines during broadcasts. They press edges together, smoothing transitions by hand and roller tools. Irrigation systems activate immediately. Fine mist sprays fall across the field in overlapping patterns.
Why so much water control? Because at this stage, the grass is not anchored. It can dry out, shrink.
Over the next weeks, the field transforms again. Roots begin to grow downward into the engineered soil layer,
anchoring the sod into a unified surface. Groundskeepers monitor moisture, temperature, and growth patterns daily.
Grow lights are deployed in shaded stadium sections, simulating sunlight where natural light cannot reach.
Large fans circulate air to prevent fungal growth and keep the turf dry on the surface but active below.
The mowers arrive for the first cut. Blades spin at high speed, trimming only a few millimeters from the top. Then testing begins. Ball roll machines launch footballs at controlled speed.
Sensors measure bounce, friction, and surface uniformity. Impact testers simulate player pressure under match conditions.
Why all this precision? Because this field will eventually support professional athletes moving at full speed,
changing direction in an instant and striking the ground with tremendous force.
Every millimeter matters. By this stage, the pitch has become a living system, ready to perform at the highest level.
What fans see on match day looks like nothing more than a layer of grass.
But beneath that green surface lies an entire network of engineering. While above it, groundskeepers work every day to keep the turf healthy and consistent.
Inside the factory, everything starts far away from anything that looks like a soccer net. Large bags of polyethylene pellets are dumped into vibrating hoppers. Inside the factory, everything starts far away from anything that looks like a soccer net. Large bags of polyethylene pellets are dumped into vibrating hoppers. Inside the extruder, temperatures rise until the plastic melts into a thick liquid. Then it is pushed through spinneret plates with hundreds of microscopic holes, forming continuous filaments. As soon as they exit, cooling systems solidify them within seconds into long synthetic fibers.
If temperature or pressure shifts even slightly, the molecular structure becomes inconsistent.
That inconsistency doesn't show up immediately, but it will cause weak points that fail under repeated ball impact later.
The newly formed fibers move into long drawing systems, where steel rollers pull them forward under precise tension.
The movement is fast but controlled. As the strands stretch, something important happens inside their structure. The molecules align in one direction, making the fibers significantly stronger, even though they become thinner.
In synthetic materials, strength is not just about what something is made of. It's about how its internal structure is arranged. Without alignment, the net would feel fine to the touch but fail instantly under repeated high-speed impacts.